Hi, purpose of this video is to help you through this electric field strength formula as seen here in our book. Before we start, let's talk briefly about electric fields. An electric field is the area that exists around any charged object, whether it's a single particle or a charged Van de Graaff generator. The field is invisible, and so we use electric field lines to show how the field behaves around that charged particle. And so here's the diagram of your book of the pink field lines around the negatively charged particle. On the next page, it's a diagram showing, again, the pink field lines, this time around a positively charged particle. Really here, the only difference is that the field lines are going out of the positive. On the last picture, they went into the negative. When we look at two particles near each other, we see that the field lines are flowing out of the positive and into the negative. Now, the field strength is how strong the field is at different places within the field. Here, where the field lines are close to each other, near the positive or near the negative, the field is strong. Out here on the edge of the field, where the field lines are farther away from each other, the field is weaker. And so we can see relative strength of the field by examining the field lines. They always go out of the positive and into the negative, and the field is always strongest where the field lines are closest together. Here's something called charge parallel plates. This would be two long parallel plates that each carry a charge. One is positive, one is negative. You'll notice that the field lines here still flow from positive to negative, with slight curves near the ends, right here and right here. But because in between the ends, the field is uniform strength, that means it's the same strength everywhere. This is shown by having these parallel field lines that are equidistant apart from each other. If we look at the field equation, again, it looks like this. The electric field, E, is the force per every charge in the field. So I have a little sketch here of a charged, let's say, Van de Graaff generator with the field lines flowing into it because it has a negative charge. I've placed two test charges in the field. Test charges are typically positive. One is +1 coulomb and one is +2 coulombs. Both of those would be being pulled towards this Van de Graaff generator. The one that would be being pulled harder would be the one with the greater charge. Just like something that weighs more is pulled stronger by the earth when pulled next to something that weighs less in a gravitational field. However, the field strength at these 2 points is actually the same amount. So the field strength is not dependent on the size of the charge placed in the field. It's really only dependent on 2 factors: how strong the actual object is that's charged, and how far away these charges are within the field. If I move this charge further away, the force on it would be less, and if I move this charge closer, the force on it would be greater. So if we go down back to this equation, E equals Fe over Q, we also have to remember that field strength is tied into distance, and that is it follows the inverse square rule. The further you get away, the 2 charges get away from each other, the less the field strength, the electric force is, So here, since electric field strength is directly proportional to the force involved, we can find these 2 things. First off, this graph here, E versus Fe, would lead to a line that generally looks like this. Now you'll notice D, or distance, or I suppose I could have also used R, is not in the field strength equation. However, because these 2 properties, field strength and force, are proportional to each other, and because force is inversely proportional to distance, we can conclude that the electric field strength is also inversely proportional to distance. And so this graph would have that inverse square curve here. And what that basically means is if I had a test charge here and I have the distance, it would have a strength 4 times greater. If I move this charge twice the distance away, the field strength would be cut in a quarter. It would be a quarter of the original strength. Now let's get down to solving this problem. It's really straightforward. The one that I'm going to sample is number 22 on the paper given. And so it looks like this. It says that you have an electric field and has a particle that has a charge, Q stands for charge, of 1.0 times 10 to the negative 5 coulombs. The force on that charge is 0.20 newtons. And what we're trying to find is the E, the electric field strength at that specific point within the field. And so I do that by using this equation. E equals Fe divided by Q. And so my Fe here, the force, is 0.2 newtons. The charge is 1.0 times 10 to the negative 5. So I'm going to, that's coulombs. Right? So I'm going to bust out my calculator and put it in as follows. Okay, so it's the force, 0.2 newtons, divided by the size of the charge, 1.0 times 10 to the negative 5. And we get 20,000. And so the electric field strength is 20,000. In terms of units, it's newtons over coulombs. So 20,000 newtons per coulomb. One little twist here is you have to remember, if we put either a proton or an electron in the field, then the size of the charge Q would be equal to the size of the elementary charge. Remember that the elementary charge is 1.6 times 10 to the negative 19 coulombs. I hope that helps. Good luck. Email me with questions.